Now, let's talk about the standard error and the asymptotic distribution of the Monte Carlo integration estimators. For now, let's return to the bounded integral setting and consider the Monte Carlo estimator theta hat, which is given by b minus a times gx bar. And here gx bar is the sample mean of the gxi's. So theta hat is an estimator for theta. An estimator is a random variable, so it has some sort of distribution, and it has a variance. In this case, what is the variance of theta hat? We earlier showed what is the variance for theta hat in the case of a equals 0 and b equals 1. So let's just quickly show this for the general case. Here, the variance of theta hat is equal to the variance of b minus a divided by n of the sum from I equals 1 to n of the gxi's. Sorry, so this parentheses should be moved here. And the variance of this thing is equal to b minus a squared divided by n squared, just we pull the scalar out and square it, times n times the variance of gx, because we know the gxi's are IID and they all follow the same distribution as x. And this is given by b minus a squared divided by n times the variance of g of x. Note that we can estimate the theoretical variance of g of x, which is given by sigma squared. By definition, this is equal to variance of g of x. We can estimate sigma squared with the sample variance of g of x. Let's denote the sample variance by sigma squared hat, or sigma hat squared. And this is given by the sum from 1 to n of gxi, the individual samples, minus the sample mean squared divided by n. So that's the standard deviation formula that you are familiar with, the variance formula you are familiar with. So if we substitute sigma hat squared into the variance of theta hat, we can get a variance estimate for our theta hat as well. And this is given by variance hat of theta hat, denoting the estimated variance of theta hat, which is equal to b minus a squared divided by n times, we substitute the sigma squared by sigma hat squared, so times sigma hat squared. And if we take the square root of this, it gives us the standard error estimate of theta hat. We denote this by SE of theta hat, which is given by the square root of var hat, and this is equal to b minus a divided by square root of n times sigma hat, where sigma hat is the sample SD of g of x. So in your 410, you probably learned about the central limit theorem, which tells us that as n goes to infinity, as our sample size goes to infinity, the sample mean minus the theoretical mean divided by the square root of the variance of the sample mean will converge in distribution to the standard normal distribution. In our case, this will mean that our theta hat minus the true value theta divided by the square root of the variance of theta hat is asymptotically normal 0, 1 distributed. Furthermore, I'm not sure whether you learned this in 410, but there's a famous theorem called the Slutsky's theorem. The Slutsky's theorem tells us that we can substitute the denominator, the square root of the variance, the true variance of theta hat, by its estimate. So the standard error estimate SE of theta hat. If we replace the denominator by the finite sample estimate, the resulting fraction over here, theta hat minus theta divided by SE of theta hat, is still asymptotically normally distributed. This allows us to find a confidence interval for our theta. So suppose that we want to find the 100 times 1 minus alpha % confidence interval for theta. Then this is given by theta hat minus z times SE of theta hat. And the upper bound is theta hat plus z, some z value, times the SE of theta hat. In this case, the SE of theta hat can be estimated from our finite Monte Carlo samples. And the z here is the critical value under the normal 0-1 distribution that we try to find. So for example, if we choose to find the 95% confidence interval, then 100 times 1 minus alpha is equal to 95, meaning that 1 minus alpha is equal to 0.95. In this case, alpha is equal to 0.05. And the corresponding z value we'll try to find will be the 0.975, so 1 minus 0.025 quantile for the z distribution, which is approximately 1.96. So this confidence interval has a 100 times 1 minus alpha % chance of containing the true theta that we're trying to estimate. So let's go back to our example where we try to use Monte Carlo integration to evaluate theta. That's given by the integral from 0 to 1 of 1 over 2 plus sine 1 over y dy. And let's try to find what is the standard error and a 95% confidence interval for our theta. So earlier in example 3.2.4, we have used the Monte Carlo integration to approximate theta, which is equal to the unbounded integral between 1 and infinity of g of x dx. I'm not going to read the g of x again, it's very tedious. And we have shown earlier using the integral by substitution that this is equivalent to the integral between 0 and 1 of 1 over 2 plus sine of 1 over y dy. So here is the earlier code that we have ran to do the Monte Carlo integration with y instead. And this is our resulting theta hat, which is the arithmetic mean of the g stars of y's. Now let's try to get a standard error estimate of our theta hat. To do this, we'll first need to compute the standard deviation of our n samples. Let's denote it by sigma hat. And then we will try to transform that, and using the formula that the SE of theta hat is equal to b minus a divided by square root of n times the sigma hat. So the sigma hat here, to implement it in R, is simply the sample standard deviation of our g stars of y's. So g star of y, recall that this is the g star function, this function evaluated at our uniform y draws. So we first get the standard deviation of the g stars, the g of y's, g star of y's. And then in order to get the standard error, we apply this transformation, and the SE of theta hat is going to be equal to 1 minus 0, so b minus a, because this is from 0 to 1, divided by the square root of our sample size, so square root of 100,000 times sigma hat, which is the sample standard deviation of the g star of y's. And let's see what is our standard error of our theta estimator. Well, this is close to 0.00059, which is really small. And that will mean that the expected amount of fluctuation of our theta hat is actually quite small from the true theta. So using this standard error estimate, we can obtain a 95% confidence interval for the true theta, which is the integral we try to evaluate. To do this, we can first find the critical value, which is z value, corresponding to alpha equals 0.05. And then we can try to find theta hat plus or minus the critical value times the standard error of theta hat. And that will give us the lower and upper bounds for the 95% confidence interval. Here's the R code that implements this. We first find the critical z value, z of 1 minus alpha divided by 2. And this can be obtained using the Q-norm function. So we want to find Q-norm with p equals 1 minus alpha divided by 2. So this is Q-norm of 0.975. And this should be around 1.96. You can check that. Now we are ready to find the 95% confidence interval. And the lower bound is given by theta hat minus z times the standard error for theta hat. And the upper bound is quite similar, but we replace minus by plus. And then this interval, lower to upper, which is from 0.4444 something to 0.4467, is a 95% confidence interval for our theta. In other words, there is a 95% probability that this interval actually contains our true parameter theta. Okay, so we have talked about how we can use the uniform density to have a simple Monte Carlo estimator for bounded and unbounded integrals. We have also seen how we can approximate the standard error for theta hat, our Monte Carlo estimator. Notice that we still haven't talked about the efficiency of our Monte Carlo estimator. We have talked about the unbiasedness, the asymptotic consistency, its asymptotic distribution, which is the normal 0, 1, if we rescale it, minus the theoretical mean and rescale it. But we haven't talked about the other property of the estimator, which is its efficiency. So next week, we will consider the efficiency of the theta hat, the Monte Carlo estimator. We will talk about the mean square error of this estimator, and we will also talk about some more advanced methods where we can try to improve the efficiency of our Monte Carlo estimator.